Good morning, students. In last video, we started the discussion about heap management and also discussed what is meant by memory manager, the memory hierarchy of a computer, and locality in programs. In this video, we complete the heap management. So, with the discussion of reducing fragmentation, manual deallocation request. So, now we start the discussion from reducing fragmentation. So, here the major scope of fragmentation is, so that means to reducing the fragmentation, obviously the memory optimizations will be increased. So for that purpose we will try to reduce the fragmentation in memory management system. So for that purpose, so at the beginning of the program execution, whatever the memory is available to executing that particular program, so that is storage, whatever the store is available, that is nothing but heap. So this heap is treated as a single memory unit or single storage unit. So it contains continuous amount of some free memory or some free space. So whenever we performing the allocations and deallocations, at that time that continuous free space can be divided into allocated space and deallocated space. So that means allocated memory and free memory. So this free memory can be divided into chunks of free memory locations. So that means so that entire memory will be divided into some small units, and these small units can be defined as maintained as a single chunk. So this chunk contains some number of free memory blocks. So at the beginning, entire memory is a single storage unit. After performing the allocations and deallocations, it was divided into multiple chunks. So that is the process. So in this process, whenever we refer to the free chunk of memory as whole, so that means each and every free chunk of memory is referred as a one whole. So here each allocation request, the memory manager must place the requested chunk of memory into a large enough hole. So that means whenever the program requests some memory, so at that time, so this fragmentation is responsible, this memory manager is responsible for providing or placing the large enough memory space for that requested program. So based on available memory holes or available enough memory holes. So in case there are available large enough memory is not available to allocating the memory space to that particular program, at that time, in case that the amount of memory space is not find, so at that time, so it needs to split same holes. So that means it need to split some holes. So that means whatever the free available chunk of holes, those can be split into the some holes and creating a smaller hole. So that means in case that particular program requires only small unit of memory, at that time it divide whatever the available chunk of holes, those can be split into some small holes and then allocate to that particular program. So in this process, when each deallocation request is processed, that free chunk of memory are added back to the pool of free space. So that means in this process, whenever any program is requesting this memory space, at that time here memory manager is responsible for allocating the large enough memory hole or large enough memory space for that particular program. In case that particular program requires only small amount of memory or small amount of memory block, at that time this memory manager is responsible for split that particular chunk of one block of chunk of memory into some small partitions and then allocate to that particular program. And then here memory manager is also responsible for when deallocation request is processed, then all deallocated memory blocks can be added to the buffer pool for providing the contiguous space. So in this process, whenever the deallocations requester returns the memory blocks, at that time actually each and every memory block is a small chunk of memory. So that is small block of memory. So to providing the large program data, that means in case any program requires large amount of data, at that time these deallocated memory blocks or deallocated chunks of memory blocks or memory holes is not enough to providing the space for that large program memory requirement. So for that purpose, here we perform the Cole's contiguous hole approach. Cole's contiguous approach. So that means it can combine or it can merges the all free chunk of memory blocks into a single chunk or single bin. So in this process, in case we are not careful, actually the free memory is available, but we are not able to providing the free memory or requested memory to the any program, due to these all are divided into a small chunk of pools. So that's why here, when possible that no hole is large enough to satisfy a future request, even though there may be sufficient aggregate free space is available. So that means whenever any program is requesting some large amount of memory space, even though our memory management having the those total required memory is available within that memory management, still also it can't able to provide the required memory to the that particular program, due to these available memory is divided into small units. For example, if any program requires 1 MB of memory, but here these each and every chunk size is either 100 KB. So and here total number of chunks is either 100. So totally 10,000 KB of memory is available, but 1 MB is not able to providing to the that particular program. Why? Because here each memory chunk is divided into a 100 KB only. So that's why it was not able to providing the space for that large program. For that purpose, here we are performing the Cole's combine or Cole's contiguous memory allocation. So it means it combines the small chunk of memory holes into the some large or some contiguous memory space. For that purpose, we are using the Cole's contiguous manager or Cole's contiguous allocation system. So that means by simply merging or combining the free chunks into some large or contiguous memory space. So and then to performing this Cole's contiguous memory space, we can use either best fit and next fit object replacement or object placement policies. So here now we discuss what is meant by best fit and what is meant by next fit, and also what is meant by first fit object placement. So to reduce the fragmentation by controlling how memory manager places new objects in the heap. So that means we are trying to reducing the fragmentation. First of all, we know how memory manager can places new objects into the heap. So based on that information, we can reduce the fragmentation. So for that purpose, we are using the best fit algorithm. This best fit algorithm is responsible for whenever any program is requires the large hole to satisfy the subsequent large request. So at that situation, this best fit algorithm is responsible for such throughout the entire memory chunk or entire memory pool. So that requested memory size of block is available within these chunks of memory blocks or not. In case available, then allocate that particular memory space, memory block or memory space to the requested program. In case this best fit algorithm fails to, that means in case that particular required amount of memory as a single block is not available, at that time we can use an alternative approach that is called first fit. So that means here whenever any program requests the memory space, at that time it checks whatever the first free chunk of memory. So that first free chunk of memory block can be allocated to the that particular program if that free chunk of memory is large enough to perform that particular program execution. So here but here first fit is also better to providing the best suitable memory allocation for any program, but here overall performance way, here best fit algorithm or best fit approach is the better to using the memory space allocation. So here to implement the best fit placement more efficiently, we can separate free space into bins according to their sizes. So that means we can separate total available free spaces into the some number of bins, either 2 bins, 3 bins, in this manner according to their size. In case some 10 memory blocks are 100 KB size, some 10 memory blocks are either 200 KB memory size. So in this process, we can combine all 10 KB chunks into a single bin, all 200 KB memory blocks into a another bin, in this manner. So based on that, whenever any program is requesting some amount of memory, in case some program requests either 50 KB of memory to allocating their program execution, at that time which can pass such information to the bins, so it can search similar bins. So whatever the bins is suitable for 50 kb, in case there is some bin exist, each and every block size is 50 kb, then from this bin one memory chunk can be allocated to that particular program. So in this manner the total memory, free allocated memory, can be divided into the several bins. So here one practical idea is to have many more bins for the smaller sizes. That means, so out of those all free spaces, we will try to allocate those bins in smaller size to better approach. Why? Because in any program commonly we are using small objects only. So that's why we will try to allocate small bins. So for example, the Lee memory manager. So this is also one memory manager in C programming. So in GNU C compiler. So it defines these bin size is 8 bytes only. 8 bytes only. Each block memory size is 8 bytes only. So that means it can whatever the free allocated memories are, whatever the free memory is available inside the heap. So such entire memory is divided into small areas. So those are each area or each memory space size is 8 bytes in this manner. So now we discuss how to performing the binning to implement the best fit chunk. So here whenever a small size requested from the Lee memory manager, just like GNU C compiler, so requested from the Lee memory manager, then there is a bin for chunks of that size only. So whenever any memory manager requested small size of chunk. So now we discuss. So binning makes it easy to find the best fit chunk. So that means whenever a small size is requested from the Lee memory manager, then there is a bin for chunks of that size only. So we may take any chunk from that bin. So in case so some memory manager can require either 8 bytes of memory. So at that time this best fit algorithm is suitable for check whatever the bin is suitable for allocating the 8 byte of memory, and then allocate some memory space from that particular bin. So for sizes that do not have a private bin, in case that requested size is not having, at the time, so we find the one bin, so that is allowed to include the chunks of desired size. So that means we find some bin, so that bin can able to allow different sizes of chunks into that particular bin. So that means that particular bin can have either some 10 blocks are 50 kb, some blocks are either 100 kb, some blocks are either 200 kb, in this manner. So out of those it can allows whatever the required memory size. In case 70, then it can prefer 100 bytes as a 100 kb of chunk memory can be allocated to that particular program in this manner. So that is either look for and select the first chunk that is sufficiently large. So that means in this process, so it can look first chunk of that particular bin. So that particular chunk is large enough to providing the space, large enough to executing that particular program, then it can allocate it to that particular program. So in case, so it may be target bin is empty. In case whenever some program is requesting some memory, so at the time, in case the target bin is empty, or all chunks that bin are too small, so that means those chunks are not able to providing the space for that particular program requested memory. So at that time we can simply repeat the search using the bin for the next large size. So that means so in case when we are using the best fit chunk algorithm or best fit approach, in this approach, in case we are not able to providing the large enough size for the requested program, so that means here all bins are having some small sizes of the chunk. So at that time we can choose the alternate algorithm, that is first fit. So alternate chunk algorithm, that is first fit algorithm. In this, so either find a chunk we can use, or we reach the wilderness chunk. So in this approach we can find the suitable chunk, otherwise we can reach wilderness chunk. So that means this wilderness chunk is request some new virtual page from the operating system and divide whatever the requested program, whatever the program required memory size. So based on that memory size, this virtual memory can be divided into several chunks and then allocated to that particular requested program. So while we are using the best fit replacement algorithm, so which is better to improve the space utilization, but it was not able to better to improve the spatial locality. So it is best for space utilization only, but it was not suitable for spatial locality. So for that purpose, we use one useful adaptation of the best fit algorithm is to modify the placement in the cases when a chunk of the exact required size cannot be found. So that means whenever whatever the exact required size of the chunk, in case the chunk is not found, at the time we use another strategy, that is a next fit strategy. So this next fit strategy is trying to allocate the object in the chunk that has last been split. So whatever the recently splitted, so that chunk can be allocated to that particular program. So whenever enough space for new object remains in that chunk, so this next fit chunk or this next fit algorithm is suitable for whenever the new space is available, whenever the new space is enough for allocating that newly requested program memory space, then this next fit is suitable. And this next fit is also tends to improve the speed of the allocation operation to compare best fit operation. So these are the details about best fit and next fit. So now we discuss how to managing and coalescing the free space. That means how to managing the free space, or how to combine the free space into some large chunk. So here, when an object is deallocated manually, so the memory manager must make its chunk free, so it can be allocated again. So that means whenever some object is deallocated, that means their execution is completed and that particular object lifetime is completed, scope is completed. At that time, here memory manager is responsible for collect such chunk of memory and then available to reuse that particular chunk by the any another program. So in some situations or in some circumstances, it may also be possible to combine the chunk with the adjacent chunk of heap. So that means in some considerations, so whatever the recently deallocated memory chunk, that memory chunk can be combined with next chunk of memory, so to perform the large chunk. So that means to providing the large chunk of memory. For that purpose, once whenever the some object is deallocates the memory, so such deallocated chunk can be continuously are added to the existing chunk of memory to become a large chunk. So why we are performing so that merging or that combining chunks means, so there is an advantage to doing in this manner. So that is always we use a large chunk to do the work of small chunks of equal total size. That means whenever some program requires either some large memory size of chunk, so at that time, so whenever we are using the small chunks for each and every memory management system, then it was not able to handling the type of situation. So for that purpose, we can combine whatever the free small chunk of memory blocks available, so that free small chunk of memory blocks can be combined into some single large chunk, so to allocating the large size of programs. But in this process, Lee manager can prefer the small sizes of chunks. So then we may prefer not to combine adjacent blocks to a larger size of chunk. So which is similar to the keep all the chunks of one size in as many pages as we needed and never never calls them. So that means, so whenever by the reference of Lee memory manager, like in GNU C compiler, so based on that memory manager, so the list of available chunks of memory can be maintained as a small chunks. So in this memory manager perspective, so that list of small chunks of memory cannot be combined as a large memory, or cannot be combined or cannot be calls them. Then a simple allocation or deallocation scheme is to keep a bitmap. So that means how we can identify any chunk is currently available or allocated to the any another program or not. For that purpose we are using the some bitmap algorithm. So that means here we are using the single bit at boundary of the each and every chunk. So based on that single bit can maintain the two values, those are either 0 or 1. So here 0 means that particular chunk is occupied by the some program. Here 1 means that particular chunk is currently free. Sorry. Here 1 indicates that particular chunk is occupied. Here 0 indicates that particular chunk is free. So based on this bitmap algorithm, we can easily identify whatever the total list of free memory chunks are available in that particular memory manager. So in this process, some tables are more complex when a heap is managed as a whole. So that means when we are maintaining total memory chunks as a single memory, a single chunk. So at that time there are some problems can be occurred. So when we are maintaining those small chunks as a single chunk or single whole memory chunk, at that time we are getting some complexes or some troubles. So we are not able to handling that particular problem. So for that purpose we are using the two data structures. So based on these two data structures we can easily handle such type of problems. Those are boundary tags and double linked embedded free list. Here boundary tags means, so at the both low and high ends of the each and every chunk, whether free or allocated. So that means it can maintains at the beginning of low boundary and high boundary. That means at the beginning of that particular chunk and ending of that particular chunk, it can maintains that particular chunk is free or allocated. So based on the bit mapping. So that bit mapping technique can be used in both boundaries at the beginning and ending, low boundary and high boundary. So based on this information we can easily keep track of the whatever the free list of memory chunks was available. And here doubly linked embedded free list means, so here we maintain some double linked list. So here each and every element is linked with next pointer. So that particular pointer can provide whatever the boundary information of the next element or previous element. So based on this information we can easily choose any free chunk of memory to allocating the memory for any requested program. And final thing, manual deallocation request. So in this session we can close with how we can perform the manually deallocation of the any program or any object. So here like C or C++ languages, ideally any storage that will no longer be accessed should be deleted. So that means, so here either in C programming or C++ programming languages, in case any object or any storage, so that particular storage or that particular object is not utilized or not used by any program until some long time, then automatically that particular object or that particular storage can be removed from the heap. So conversely, any storage that may be referenced must not be deleted. So in this process that particular object is referenced, that particular object or that particular storage is referenced with any procedure or any function. So at that time we can't delete that particular storage. But here unfortunately which is hard to maintain such type of properties. So in addition to this, considering the difficulties with manual deallocation, we shall describe some of the techniques or programmers used to help with the difficulties. That means whenever we are performing the manual deallocations, in this process we are facing the several difficulties. To handling such difficulties we can use some tools. So some tools. So those are especially three tools. So those are object ownership and reference counting and region based allocation. So here while we are using the manual object deallocation, at that time we are using the some conventions and tools. So now we discuss whatever the several conventions and several tools was used for performing the manual deallocation of the space. So now we discuss several most popular conventions and tools that have been developed to help the programmers to performing the complexity in managing memory. So those are object ownership. So this object ownership is useful when an object lifetime can be statically reasoned about. So that means this object relationship is defined whenever any object lifetime is statically reasoned. So that means that particular object time is fixed, that never change. So at that time the owner of that particular object is responsible for deleting that particular object, otherwise passing that particular object to the another object or another function, that is called another owner. Here owner means some function. So whenever that particular object time or that particular object utilized by the that owner or that particular function is completed, then that owner is responsible for passing that particular object to the another owner or deleting that particular object from the memory space. So which is possible to have other non-owning pointers to same object. So that means so that particular object can be transferred or passed to the another function. So that means actually that function doesn't have that particular object, that means which is not owner of that particular object, still it can able to accessing that particular object until completion of their execution or their work. So this convention eliminates memory leaks. So this type of memory this type of algorithm or this type of processing is overcomes the elimination of memory leaks. So it can overcomes the memory leaks as well as attempts to delete the same object twice. So that means with the help of this technique we can overcome whatever the drawbacks or whatever the problems with memory leaks, and at the same way whenever we are trying to delete some specific object by multiple times, such type of problems can be overcome with the help of this approach. Object reference, object counting. So and the next tool is reference counting. So here actually in previous one object ownership, we are confused whenever that particular object is owned by more than one owner or more than one function. At that time we can't able to estimate that particular object is currently accessed by any owner or any object, any function or not. So that is the problem. To overcoming from that problem we are using the reference counting. So that means once any object is created with until lifetime of that particular objects, it can be determined dynamically, previously statically. Here we can use or we can determine that particular object dynamically. So that means the idea is to associate a count with each and every object dynamically allocated. So that means here once that one object is created, so that particular object can maintain some dynamically accessed by the any owner or any function with the help of some count function, some count option. So that means some reference count. So here whenever that particular object is accessed by the any function or any owner, then their count is increased by 1. Whenever that particular object is deallocated from the any function or any owner, then decrement the count of that particular variable. So by using this technique, it doesn't catch useless. So that means that particular data is not we says that useless, because so circular data structures, either with the help of this mechanism we can use the circular data structures where a collection of objects cannot be accessed, but their reference counts are not zero since they refer to each other. So that means by using this technique we can't able to eliminate or we can't able to removing that particular object until getting their count reference is 0. So that means in case that particular whenever we are trying to deallocate that particular object, so in case the reference is more than 0, that means either 1 or 2, then we can't able to remove that particular object. So in case that particular object reference is 0, then we can remove that particular object, we can deallocate that particular object from the memory space. And final thing is region based allocation. So this region based allocation is also useful for collection of objects whose lifetimes are tied to specific phases in a computation. So that means this mechanism is especially helpful for whenever we are creating some object or whenever we are allocating some specific object, that particular object is suitable within some phase of a computation or some phase of a program. So when such objects are created by using only within some step of a computation, so we can allocate all such objects in the same region. So that means whenever we are creating some object, so that particular object can be accessed by within some region of the memory space only. So this region based allocation technique has limited applicability. So actually this region based allocation technique was very little times or very little time applicability, limited applicability only. So that means, however, which is very efficient whenever it can be used instead of deallocating the objects one at a time. So that means whenever we are trying to accessing the some new objects, at that time this region based allocation is suitable. But after completion of that particular object, so to eliminate or to remove or to deallocate that particular object space, which was some complex in regional based allocations. Why? Because once we clear that particular object or once we deallocate that particular object, it may not be useful for any another region. That particular object is useful within that particular region only. So that's why sometimes it was not useful. So these are the several tools while we are using the manual deallocation of the space. With the help of these tools, we can easily implement or performing the manual deallocation. So these are the details about heap management. Thank you.